Hello, my name is Chinmay Harmalkar and my project is based on the alternating tripod gait which has been inspired from an ant. Firstly, I'd like to discuss why I chose an ant as my inspiration. Secondly, I'd like to talk about the anatomy of an ant and what makes ants unique. I would later want to move on to the analysis of the gait which has been performed in the recent years. I'd like to move on to the gait model that I have developed in MATLAB and finally end with the conclusions. So, why did I choose an ant? An ant is an arthropod. Arthropods are animals which have segmented bodies with exoskeletons, which makes them pretty robust. This allows them to carry heavy loads at consistent speeds over rough terrain. As you can see, that itself inspires the idea of building a robot which imitates them. Moving on to the anatomy of an ant. As you can see, the body of an ant is mainly divided into three regions: the head, the trunk, and the tail. As you can see, all the legs are connected to the trunk of the ant, which is also known as the thorax. Moving on to the leg structure of an ant. As we can see, it's mainly divided into three regions. The coxa is the part which is attached to the thorax, which allows the first degree of movement. The joint between the coxa and the femur allows the second degree of movement, and the joint between the femur and the tibia allows the third degree of movement. The alternating tripod gait is called so because the ant uses its first and last leg on one side and the middle leg on the other side to literally put down tripods. The center of mass, which is denoted by the triangle, falls within this tripod, making it a statically and dynamically stable gait. As you can see, while moving, the center of mass moves from the previous tripod to the next tripod. The alternating tripod gait undergoes many variations. The primary variation is due to the addition of load. The ant carries most of its food articles on its head, which causes the center of mass to move to its head. As you can see, figure A and figure B, it would be dynamically impossible to carry a load and walk if the center of mass is on the head. So, to even these things out, the tripod is distorted by moving its hind leg and the middle leg further away from the body and allowing the tripod to extend. Although this reduces the stride length of the ant, the speed of the ant remains the same. The next variation is due to the speed of the ant. As you can see, speed actually does not cause any spatial distortion in the tripods. It just varies the placement of the tripods. As you can see in figure A, the tripods are placed much closer together, which allows us to conclude that the ant is moving at a lower velocity. Whereas in figure B, it's moving at a much faster rate, allowing the tripods to be placed further away from each other. The next variation is when ants walk on curved paths. During curve walking, ants use comparatively conservative strategies. Distances between successive footfalls on the inner side are shortened, whereas on the outer side they remain unchanged. As a result, the spatial tripod pattern is maintained even when the ants walk around narrow curves. Next, we move on to the gait model which has been implemented on MATLAB. As you can see, each joint has been assigned a frame and the leg is being treated as a robotic arm. As you can see, joint angles have been assigned to every joint, making it relatively easy to give angular displacements and find out the final position of the leg. This is a static model of the ant which has been developed on MATLAB, As you can see, it has 6 legs and only the thorax has been simulated. As you can see, the tripod gait is being simulated in MATLAB as shown in the video. As you can see, the tripod is being formed by the tips of the legs, and though it's not an accurate rendition of the tripod gait, but it still gives us a fair idea how it works. In conclusion, I'd like to say that the alternating tripod gait is a stable gait both dynamically and statically. The energy cost for implementing an alternating tripod gait on a plane surface is much more than that of a wheeled system, but on rough terrain it would always be a better option. We can always use image processing, localization techniques, and other sensors to traverse the terrain more efficiently. Also, the implementation of gait variations, which has been observed in ants, always help them to traverse rough terrain efficiently. If we were to implement all these variations in an actual robot, we would be able to harness maximum efficiency from the robots. Thank you.